Okay, so in this video, we're going to look at simple harmonic motion. Remember, the last video just kind of defined some key terms that you're going to hear over time. So the first thing we're going to talk about is simple harmonic motion. So what exactly is simple harmonic motion? Right. So simple harmonic motion is the periodic motion. I'm sorry, it looked like I was starting to write a T. So it's periodic motion that is caused by a restoring force. A lot of times we'll just call it SHM. So again, there's that term of restoring force. Another way to think about it is that it's motion about an equilibrium position, right? And so equilibrium means where forces aren't acting on it. And so this is what all pendulums and all springs want to go back to. Now, what happens is the motion itself can be modeled as a sinusoidal function. Okay, and a sinusoidal function, if you're in pre-calc, you've taken pre-calculus, sinusoidal function just means it's a sine curve. So it's a repetitive curve. If you remember sine curves, they look stuff like this, right? They go up and down, up and down. Well, you can also have a cosine curve, which starts at the maximum and goes kind of opposite, right? I know those are bad, functions there, but that's what we mean. It's repetitive. It's periodic, right? So when an object in simple harmonic motion is unaffected by friction, uh, okay, and under these conditions, will continue indefinitely. So the reason why, again, in physics one, we assume ideal conditions, so that spring is going to keep going up and down, or that pendulum is going to keep going back and forth. Okay. If it does get affected by friction, it's what we call a damped harmonic oscillator or a damped harmonic motion. Right. Now, in physics one, it's only tested qualitatively, right? So they're going to talk about it, right? They're going to talk about general observations, but it's not quantitative. You're actually not going to calculate anything with it. All right. Now, the two main examples of simple harmonic oscillators that we talk about in physics one is the simple pendulum and the mass spring system. Now, the thing about the mass spring system is we will do vertical mass spring systems and we will do horizontal mass spring systems, right? So the vertical goes up and down, horizontal goes left and right. Okay, and so here are just these two oscillators, and we're going to talk about just some key points about these oscillators before we go any further. So the pendulum, right? This lowest point is our equilibrium position. So when we talk about the restoring forces, this is the position that it wants to come back to. The way we also think about it, this is when the height is equal to zero. And if you remember anything about energy, when the height is equal to zero, the energy at the lowest point of the swing is all kinetic, which means its velocity is at a maximum. Okay. Um, this also means that our acceleration will be zero. Now, the extremes, when I say extremes, I'm talking about this point and this point. So what I'm about to write applies to both of these points, right? And so this is when it's at its max height. So the furthest away from its equilibrium position, which means this part right here is going to be at its highest. The velocity is going to be zero, right? The restoring force wants to stop the object, right? Stop that bob and have it come back the other way, which means the acceleration and the force are going to be at its max, right? And so if it's at its maximum height, it's going to be all potential energy. Okay. And then in between these 2 points, it's a mixture of kinetic and potential. Right. And so to calculate the acceleration at that site or at that point, it's going to be A equals negative G sine theta. And the theta will be the angle that it makes up here at the vertical, which makes the force, the restoring force, negative mg sine theta, right? And so the way you think about Why is it negative? It's because they have to work against each other, right? So if here it wants to go this way, right? And before you get to this point, it still wants to move to the, kind of up and to the left, which means this acceleration has to go down and to the right. Same thing on this side. This wants to move up and to the right. This acceleration has to move down and to the left, right? They work against each other, right? Now, all this can be equated over to the mass on a spring system, right? So this is our equilibrium point. Again, everything holds true, right? This is when the elongation is zero, which means the acceleration is zero, that it's all kinetic energy at this point, which means our velocity is at the max, right? Which also our force is zero. And I could write that over here too. So F equals zero, right? These 2 points, what we call the max amplitude, right? Or when X is at its max, okay? These are like our extremes. And so this matches all of our extreme stuff, right? So it's at a so max amplitude, the velocity equals zero, right? So in this case, it wants to move down, the restoring force goes against it. Same thing here. It wants to move up, but the restoring force goes away from it. So this would be like F and A, right? This is F and A, and this is our motion, okay? Um, and so that means that, again, our force and our acceleration, right, are at its max. I don't know what to write A equals X, but so this is when A is at its max. Now, for a spring, force is at its max when it's negative kx, Hooke's law, right? We talked about that in the last video, which makes our acceleration equal to negative kx over m. And the m is the hanging mass, okay, or the mass that is attached. Because I could take this and flip it on its end, and it behaves the same way, right? So when I'm tight, right, equilibrium, and then when I'm kind of fully stretched out, right? I mean, that's this point, this is this point, and that was that point, right? And so let's look at a quick example. Looking at some of these, like the spring force and acceleration. Okay. Um, so here we have a 2 kilogram mass attached to a spring and is allowed to travel on a frictionless table after being stretched a distance of 50 centimeters. This is important that we do have a frictionless table because then we can just, don't have to worry about any effect of friction, right? We don't have to really do a free body diagram, which way is, friction acting and everything. The spring is going to be attached to a wall, which is going to allow it to go back and forth. The spring has a spring constant of 100 newtons per meter. Calculate the maximum spring force and the maximum acceleration of the 2 kilogram mass that is attached to the spring, right? And so all this is at its max when it's stretched out. So we're going to say when it's at 50 centimeters or 0.50 meters, right? So F spring negative kx. In fact, we're going to call this just kx. We're going to just look at it. We're going to call it the absolute value, right? We just want that the magnitude, if you want to say. So we're going to do 100 times 0.50, all right, which gives me at the extreme a max of 50 newtons. Okay. Now, if we go to the acceleration side, on the in the right before we got to this problem, we did A equals negative kx over m. Again, I'm going to take this because we're just really want to look at the magnitude of it. Well, we figured out what k times x was. It was 50 newtons, right? And then we know what m is. It's 2 kilograms, okay, which tells us that we have a maximum acceleration of 25 meters per second squared, right? And technically these would be negatives, but we're going to look at just the magnitude of it. So in the next video, we're going to focus on the period, right? We're really dive into one of the main topics for this unit, which is the period of simple harmonic oscillators.